In this series, we explore competing models for what happened at or even before the Big Bang. In classical physics, black holes and the Big Bang both feature singularities, points of infinite density and curvature where time no longer ticks. Is this similarity just a coincidence, or is there more to it than that? Was our universe born inside of a black hole? In this film, we'll investigate several models that explore this intriguing possibility, starting perhaps with the most well-known version, a proposal inspired by Darwin's theory of evolution, CNS, or Cosmological Natural Selection.
Cosmological natural selection is a theory aimed to answer the question, what determines all the different parameters of the standard model of particle physics?
It is often said that if those parameters were to take different values, then atoms would not be able to form, and higher structures like galaxies, stars, biological systems would not form in the same way that they do today. And in fact, if the parameters were different, then the universe would be inhospitable to life.
I saw this as a problem akin to the problem of biology, which is to explain why the different creatures in the living world are so fit. If you imagine that the parameters of the standard model are like the genes, then with different choices of the genes, you get different organisms in different ecosystems with different populations of organisms. Compared to most random changes, to most random mutations of the genes, the animals or the organisms are fitter than they would be under a random change. This seems analogous to the claim that the universe is more complex and more hospitable to life for the present values of the parameters than for random values of the parameters. So I wondered whether there could be an explanation akin to biological natural selection, which would apply at the scale of the universe as a whole. And I was reading some of the evolutionary biologists, Steve Gould and Lynn Margulis and Richard Dawkins and others. And this very, very much impressed me, how clean an understanding you got about the fitness of the organisms, the animals, and the plants from natural selection. And I wondered whether you could make use of the same method of explanation in cosmology to explain the parameters of the standard model.
Cosmological natural selection offers the idea that a new universe comes into being at a singularity of a black hole. Each universe is equipped with a set of parameters, the parameters of nature, that govern the physics in that universe. And the parameters change a little bit between the parent universe and the new universe. There is a set of parameters, it is postulated, that maximizes the number of black holes formed in a universe, in a given universe, and therefore maximizes the number of progeny that it produces.
In CNS, it isn't life that the universe is selected for, but black holes. As black holes are often formed from stellar collapse, and the existence of stars is the key to life, life becomes a happy byproduct. But evolution also needs reproduction, and so this hypothesis relies on the idea that black hole singularities are replaced by some form of bounce.
That idea came from early workers in quantum gravity, people like Bryce DeWitt, who was my postdoctoral supervisor for my first postdoc, and John Wheeler. And they hypothesized that the singularity, which is at the interior of every black hole in general relativity, is removed by quantum effects and replaced by what we call a bounce, where the collapsing material inside the horizon of the black hole bounces and begins to re-expand. But there's nowhere for it to go. If it can't get out past the horizon, it can't get back into the universe in which the black hole originally formed. So it forms, it kind of punches its way into forming a new region of space and time called the baby universe. And this baby universe can expand, and that creation can be very like the Big Bang of our universe and lead to the creation of a new universe. So that idea was not new. That idea it was described to me by Bryce DeWitt when I went to work for him in Santa Barbara. And he said, this is a thing I think about a lot, maybe you can do something with that. A second idea, which was also not my idea, was Johnny Wheeler's idea, that when that bounce happened, the parameters of the standard model came out differently afterwards. They changed. The only thing I added to Johnny's model was the assumption, and it is an assumption, that the change is small in each generation. And that's very important, because if you're trying to increase fitness by discovering through trial and error the best value of some parameter in terms of its effect, in this case making black holes, if you move in small steps, you can get closer to the maximum. If the steps are too large and random, you'll never discover those special values that lead to many, many universes being created.
While the motivation for CNS is the apparent fine-tuning of the universe, one of the creators of our next model, the holographic Big Bang, is less persuaded that such fine-tuning is real.
What is fine-tuning is really philosophical, because people talk about naturalness, but at least it's one way that physicists try to quantify fine-tuning. But of course, naturalness implies that you know what is natural. And as we are kind of developing the theories of nature, how do we know what is natural and what is not natural? If you bring life to the issue, it becomes hugely more complicated, because we only know of one type of life, at least intelligent life, which is our own. Who's to say that if the universe didn't look very, very differently, there wouldn't be a very, very different type of life that developed there? So maybe if you just have a complicated enough system, doesn't matter what your fundamental constants are, you're going to develop some type of intelligent object. Certainly, when it comes to life, I think it's very vague. It's hard to buy. But even independent of that, whether some constants are too small or not, yeah, I think the evidence that there is fine-tuning is very subjective.
Lee Smolin has responded that these criticisms are essentially aimed at the anthropic principle, which has little bearing on CNS, as CNS only requires local changes in the parameter space. Nevertheless, both Smolin and Ashfordi agree that our universe may have its origin in a black hole.
So black holes are kind of big bangs but reversed. So what black holes are, if you think about like a star collapsing into a black hole, you have a star that's kind of getting smaller and smaller, and there's really nothing that could prevent it if with the right condition. If you are big enough stars and it runs out of all the fusion material, it gets smaller and smaller, and nothing can stop its collapse, and at some point basically it collapses into a singularity. At least that's what general relativity tells us. Now, big bangs are exactly the reverse of that. You have a singularity, or you have some very, very hot, dense phase of matter that is expanding and getting lower and lower in density and temperature and pressure. So in a more abstract sense, black holes are singularities that sit in our future, because not everybody's future, but everybody who falls into a black hole, their fate is a singularity. The Big Bang, everybody who lives in a Big Bang universe, a Big Bang cosmology like you and I, our origin is a singularity. Okay, so how can you kind of relate these two notions to each other? The idea is that maybe Big Bang is like a supernova explosion, if you want. So basically you have a star in one higher dimension, or something that we call a star. We don't really know how stars in higher dimension would look like, but something that we call a star that is collapsing, and it would basically almost make something like a black hole, but then there was a membrane that comes out of it. The thing that you could predict is the properties of that membrane that comes out, and whether there are density fluctuations on it, we can calculate, at least with some assumption. Now, why you needed to increase the number of dimensions, that's the technicality, because we observe our universe to be very uniform. And a black hole itself, or a star itself, is not very uniform. The center of a star is much denser than the boundary. But if you imagine a layer or a membrane that surrounds a black hole, that could be very uniform. And in fact, there is this thing called Noether theorem that tells you that the horizons of black holes, or just all the geometry of black holes, if you wait long enough, they become very, very uniform. Now, it doesn't matter how you start it, they always go to become the same thing, essentially, up to like 1 or 2 parameters. So that's so-called no-hair theorem. So then the idea was that if you had a membrane that kind of, that hugged the horizon, that just surrounded the black hole, then that would look very uniform as our universe does. Right? So that could be, in a sense, a way of addressing the cosmological horizon problem. How do you make universe very uniform? If it had started from the horizon of the black hole, then it would look very uniform. And we know that from just classical general relativity. So holographic principle is the idea that if you have a theory that has gravity in it and quantum mechanics in it, so a theory of quantum gravity, which we think we have in our universe, then all the information and dynamics that goes on in that system can actually be read off from dynamics on a theory on the boundary of that system, which doesn't have gravity, it just has quantum mechanics. And the reason it's interesting is, it is really a conjecture, but we have evidence for it. For example, the earliest one comes from Hawking's derivation of black hole entropy. He gave very plausible arguments that black holes have entropy that goes as the area. Of course, black holes are three-dimensional objects, but if their entropy goes as the area, for most objects we know that don't have gravity, their entropy goes as their volume. The bigger they are, the more entropy they are. For black holes, it goes as their area. So that suggests that maybe all the information is on the boundary. A lot of papers, at least I started around 10 years ago, talking about how fluid mechanics, like the water in the river, act similar to mergers of black holes, for example. So, and this is very specific. So you put a membrane just outside the black holes, and then look at what that membrane is doing. And it appears that what that membrane is doing looks exactly what the water in the river does, right? It acts like an incompressible fluid, basically a fluid that's almost constant density. And that was kind of very puzzling and curious and interesting. And then with me and my colleague, and it was a student, Razia, we were trying to make sense out of this so-called, what they call fluid gravity correspondence. So usually people think about like boundary is some hypothetical place you use to do calculations, but we happen to see it in the gravities. Of course, we do see a gravity. So we kind of try to turn this around and say, what if we are in a boundary and the real universe where real gravity is farther out there in one higher dimension, and then in this context, then we could, what if then that membrane is really sitting outside the black hole where the fluid is, could that fluid be something like dark energy, I don't know, or dark matter. So those are the ideas we were playing with.
A third route to black hole genesis comes from considering a sort of twisting of space-time called torsion. Normally in relativity, it's assumed that the torsion of space-time is zero. But Cartan developed theories where this assumption is relaxed. In the 1960s, Stephen Hawking's PhD supervisor, Dennis Yama, and one of the inventors of the Higgs mechanism, Tom Kibble, showed that torsion can explain the intrinsic spin, or angular momentum, of fundamental particles.
I was reviewing the literature and I found that Lee Smolin suggested in 1990 that final singularity in a black hole could become an initial singularity for the Big Bang, for the universe. And although this was based on general relativity and still had the singularity problem, but there was already the connection, and I liked it. And from this, I was also investigating literature about Einstein-Cartan theory, how torsion can avoid singularities. So this picture came to me suggesting that torsion may be an object which allows to connect the collapse of a black hole with the Big Bang without singularity. This connection avoids the singularity. Of course, we have some super hot and dense state, but it's not singular anymore. So everything is physical. And that's basically how I started researching cosmology with like big bounce cosmology with spin and torsion.
In 2004, David Garfinkel performed numerical simulations without torsion, showing that the interior of a black hole will contain points that behave like a tiny isotropic universe.
So now, it will be interesting to repeat those numerical simulations with torsion to see how every point in the interior of the black hole locally evolves like a small universe towards not singular state, but something dense, and then there will be a bounce, which means we would have like several probably bounces, and eventually the whole interior would basically evolve on the other side of the event horizon as new baby universe. I know that numerical simulations for general relativity already say that, and torsion removes removes singularity and it is repulsion. So combination of those two effects, in my anticipation, would make it so that a black hole would become essentially a wormhole to a new baby growing universe on the other side of the event horizon.
Another mystery of the early universe is why was there so much more matter than antimatter?
Torsion introduces some asymmetry between behavior of matter and antimatter particles. So in 1970s, it was discovered that Dirac equation, the relativistic quantum mechanics equation, in the presence of torsion becomes nonlinear. There is a cubic term which comes from torsion. And then, in my paper, I argued that this term changes the sign under charge conjugation operation, which means for matter and for antimatter, this term would behave differently, which means my guess is that at extremely large densities where torsion is important, there will be some asymmetry between matter and antimatter, but when the universe very quickly reached densities where torsion became weak, then this asymmetry is basically insignificant. There are some recently discovered asymmetries with charmed quarks, mesons. But I think that physicists are saying that those effects are not big enough to explain the asymmetry. So I hope for torsion, but I would love to research this further.
While torsion modifies gravity, most physicists feel that a more fundamental quantum theory of gravity is needed to fully resolve the singularity. But why is this so difficult?
Well, there are two reasons. One is that there is very little observational evidence that we can go by. So the way science evolves is you have some observation, you try to explain it with a theory. The theory then has new predictions, which you verify with further observations and so on. But the energies at which we expect quantum gravity effects to come in are just so high that we can't reproduce them in the laboratory. So that makes observation very difficult. And the second problem is a theoretical one. The problem of quantum gravity really pushes the theoretical framework and the mathematics that was developed to a limit, and we need new ideas and new mathematics to talk about quantum gravity.
There is good evidence in several different approaches to quantum gravity and a variety of different calculations that in a quantum theory of gravity, the Big Bang singularity is replaced by a bounce. Not least of them is loop quantum cosmology, where Martin Bourgeois originally and Abhay Ashtekar and many others since have shown in those models that there is always a bounce and there's never a singularity.
That loop quantum gravity also recently predicted a big bounce, but it was not by introducing repulsive gravity from spin, but by introducing the maximum density matter can achieve. And so the dynamics is a little different, but I see conceptual similarity. So possibly, so I see actually some future in maybe combining research with Einstein quantum gravity with loop quantum gravity and see what happens. I know loop quantum gravity is quite popular. Einstein-Cartan was abandoned for like 50 years because it was overshadowed by string theory or some other theories of gravity, but it looks like now it has more and more researchers. So I hope for some connections.
As Lee Smolin is one of the founding fathers of loop quantum gravity, one might expect it to be the key to black hole genesis. But the loop community has focused more on the idea of our Big Bang coming not from a black hole, but from a previous mirror image of our universe that collapsed and then bounced into our expanding universe. However, another quantum gravity proposal called Causal Set Theory may provide the link between quantum gravity and CNS. Causal Set Theory abolishes the space-time continuum and replaces it with a discrete set of space-time atoms.
So in Causal Set Theory, this collection of atoms has some kind of order. The atoms are organized in a certain way, and this order contains all the information about whether two events are related or not. Unlike the usual atoms that we're used to thinking about, each atom has a four-dimensional volume. It is not an atom of space, but an atom of space-time.
Causal sets relies on the idea that space is fundamentally discrete, that is, discontinuous, and in this framework you just implement at a very fundamental level a so-called partial order relation. Partial order means that you put somehow by hand causality. You can say that order plus number gives you geometry. So this is really the way geometry emerged from the causal set viewpoint.
In our film on loop quantum gravity, we found that theory also assumes that space-time is made of discrete atoms. So how is causal set theory different?
So we consider a causal set, which is some kind of lattice, it's a mathematical object. We consider that to be the fundamental description of space-time and not the geometry as being fundamental. We consider the geometry as being derived, being a manifestation of this causal set.
This is, to my knowledge, the only theory of quantum gravity that has been able to make a prediction that has been confirmed after. And this was a very nice prediction about the value of the cosmological constant. We know now that there is in our universe a cosmological constant which is positive, non-vanishing, but extremely small. And impressively, in causal sets, they were able to predict this extremely strange and teeny value of the cosmological constant before it was measured.
One of the key ideas that Raphael Sorkin used in his prediction of the order of magnitude of the cosmological constant is to assume that it is in fact not a constant. He assumed that there is some mechanism that drives the cosmological constant to zero, but that in fact the value of the cosmological constant fluctuates around zero, and so it changes over time and is not constant. It's not literally constant.
If dark energy is not a cosmological constant, but instead something that changes over time, this has huge implications for the fate of our universe, which is normally assumed will expand forever. If it could turn negative, then the universe might recollapse, giving us a cyclic cosmology. But CNS is less of a cyclic model and more like a self-reproducing cosmology. So how are the two connected?
Cosmological natural selection on its own is not a fundamental theory of quantum gravity, but it could potentially be realized within a quantum gravity framework. And so Faye Dowker and I studied whether cosmological natural selection could be compatible with causal sets theory. So there were two parts to our work, and the first was to identify what would a black hole singularity look like within a causal set. One idea was to only have one space-time atom as the singularity, because in a sense that is the smallest that you can get, right? That what can be more collapsed than one atom. A second idea was to have a partition of the causal set into two parts, because in a way the singularity is what separates the mother universe from the progeny. Once we defined those structures, we studied the dynamics of causal sets around them. So the dynamics in causal set theory is given by a set of parameters, which in this model play the role of the parameters of nature. And we've shown that there is a process of change. You can repackage the parameters in a different way on each side of the partition or in each universe. And so this idea of changing of the parameters of nature across a singularity was echoed in those ideas or was shown in our work.
As the holographic Big Bang model uses extra dimensions, does it depend on the truth of string theory?
They are really independent. None of us were string theorists. I mean, the idea of having membranes, living on membranes, this was popularized by string theorists because they had constructions like that. They had basically they ended up at some point with solutions where you have strings that were all constrained. Their tips were moving on a brane. They called them D-branes. But we kind of borrowed that construction and ran away with it. So that, I mean, it could, I'm not even sure whether our construction is consistent with the string theory. But part of it is that the string theory is such a complicated theory, it's hard to really make definitive statements in it.
Any scientific hypothesis must make contact with observations if it's to move from plausible idea to accepted fact. One prediction of CNS involves the mass of neutron stars.
One of the predictions involves the collapse of a very heavy star after its supernovas, where a remnant is left, and the remnant can become either a neutron star if its mass is below a certain limit, or if it's above that limit, it becomes a black hole. And that limit is we call it the upper mass limit for neutron stars to form. And clearly, our scenario wants that upper mass limit to be as low as possible, so that more massive stars would have remnants which were over the limit and became black holes rather than neutron stars. So nobody actually knows where that limit is. When I made this argument, the heaviest known neutron star was 1.4 times the mass of the sun. And there were models of the interior of a neutron star that put that upper mass limit somewhere between 2 solar masses and 5 or 6 solar masses. So there was a lot of freedom because not much was known about the properties of the nuclear material that made up the neutron star.
Lee Smolin stumbled upon an argument based upon the work of the great astrophysicists Hans Bethe and Jerry Brown, which implies the upper mass limit of a neutron star is related to the mass of a particle known as a kaon, which in turn depends upon the mass of a fundamental particle called a strange quark.
You can imagine nature doing an experiment where the mass of the strange quark was varied to make it as low as possible, which brings down the mass of the kaon, which brings down the upper mass limit. So nature has the opportunity to have a low upper mass limit and therefore have more black holes. And one can reason that if this process of cosmological natural selection has indeed taken place, then that's how it should be. And we should go out there and measure the masses of neutron stars and not see any over some low mass, which is that limit. Now, I haven't yet said what that limit is. At the time they did their calculations, with the knowledge that was then available, they got about 1.6 times the mass of the sun. More recent calculations with more sophisticated assumptions get about 2 times the mass of the sun. And so that's the one we have to compare with the data. Now, there are different ways of measuring the masses of neutron stars, some of which are very accurate and some of which are less accurate and result in big uncertainties. All the ways of measuring accurately the mass of neutron stars agree with this prediction. There are a few values from the less precise methods up at 2.5 and 3 and so forth, but they're not cases which are strong enough to rule out the theory.
Recently, studies of gravitational waves have given independent reasons for putting the upper mass limit of neutron stars close but slightly above the 2 solar mass mark. But a neutron star has been found that lies dangerously near to that upper limit and above the limit set by Smolin. So if it's confirmed by follow-up studies and the error bars are reduced, this could spell trouble for CNS. However, philosopher Rüdiger Voss has claimed that while most universes should be optimal for black hole production, it doesn't follow that our universe is, which could call the neutron star mass limit prediction into question. Inflation is the rapid period of expansion, believed by many cosmologists to have happened in the early universe. It's usually thought to be driven by a scalar field known as the inflaton. There can be single field or multi-field models, and the way the fields evolve can have different shapes or potentials, leading to different models of inflation.
If cosmological natural selection is true, then the forces that cause inflation to take place have to have the simplest mathematical form possible, and they have to only involve one new particle, not several new particles. Cosmologists would say that you require the inflation model that describes the actual universe to be what they call single field, single parameter inflation. And that is testable experimentally, and my understanding is that it's still holding up, although it could be refuted again by any new measurements of the cosmic microwave background.
At first, cosmology with torsion was thought to remove the need for inflation altogether. But recently, Nikodem Poplawski has suggested that rather than replace inflation, torsion might drive it.
And we do not assume any scalar fields. We only assume torsion, nothing, no hypothetical fields. So what we did was that after we found out by numerically solving the equations how universe was expanding at the early times, we found out what would be a hypothetical scalar field, what would be the hypothetical potential of the scalar field, which would give us the same dynamics. And we found that scalar field, and then we put that scalar field into equations which we can compare with cosmic microwave background data, and we found that for quite nice range of the particle production rate, which is the only unknown parameter in our model, we got consistency with things like scalar spectral index or tensor to scalar ratio. So we are consistent with cosmic microwave background, and actually most interestingly, this hypothetical equivalent scalar field, which would give the same dynamics as cosmology with spin and torsion, has a shape of plateau. And right now, this plateau shape is right now the most favored potential by Planck 2013, I believe.
While CNS and cosmology with torsion seem to be compatible with inflation, the holographic Big Bang is advanced as an alternative to inflation. But inflation is thought to solve many cosmological puzzles. We'll provide the link to our film on inflation below for more on these puzzles. But one example is that high-energy physics seems to predict that the universe should be dominated by exotic particles called magnetic monopoles, yet we don't see them. Another is, why is the universe so extraordinarily flat?
You have these theories that are kind of more general and unify all the forces of nature, but they have these monopoles in them. Whether those theories exist at temperature like 10 to the 50, well, at very, very high temperatures, by I think 10 orders of magnitude bigger than anything we've ever seen. But our universe never had to be that hot, so there's no need to actually produce any monopoles that you need to get rid of. And the flatness problem can be solved actually in the same way as a horizon problem. If you have a big enough black hole, then its horizon would have very low curvature, and that would be exactly what we see.
Perhaps the most important success claimed for inflationary cosmology is its ability to explain the nearly scale invariant fluctuations seen in the cosmic microwave background. So any competitor theory must be able to do the same.
That if you just look at thermal fluctuations in 4 dimensions, which is one higher dimension that we have, so thermal fluctuations, of course, are on very small scales. But if you look at the gravitational fluctuations that are caused by those thermal fluctuations, they are scale invariant, and that was very surprising. It just comes out, there's something special about 4 dimensions. So that's of course what we see, the fluctuations of gravity on larger scales that we see are scale invariant. That if you have a thermal atmosphere that's falling into our membrane, so basically the idea is that this star as forms, it doesn't all fall in at the same time. It has basically some late infall, and it could have random thermal fluctuations. So we could actually then imprint those fluctuations onto the membrane, and it has the right spectrum. So the idea is that then you could just completely let go, get rid of inflation. This could be the whole deal.
In our film on inflation, Alan Guth claimed that inflation is generically eternal, implying that inflation doesn't just produce one bubble universe, but instead an infinity of bubble universes, generating a multiverse in what is called eternal inflation. As CNS also leads to a huge ensemble of universes, how are the two schemes different?
Both cosmological natural selection and eternal inflation generate a big set of universes, a bit large ensemble of universes, but they're very different ensembles. In cosmological natural selection, every universe in the ensemble, or almost every universe in the ensemble, has to have the property of being incredibly fit. In cosmological natural selection, you have an ensemble in which almost every universe is fine-tuned to make as many black holes as possible. So they have a common property, which our universe also shares. And the way in which you make it a predictive theory, even if it's a theory about ensembles of universes, only one of which we inhabit, is that the scenario predicts that every universe in that ensemble has a property which is checkable in our universe. In eternal inflation, you generate an ensemble of universes, none of which have properties in common with our universe, almost every one of which is strongly different from our universe. And so you don't have available to you the notion of typicality, which makes it possible, even if we only observe one universe, to test a hypothesis about it.
While we're contrasting these similar cosmological models, it's worthwhile clarifying the key difference between CNS and the holographic Big Bang.
I think the difference is that Lee's model, the new universes are inside the black hole, and ours is outside. So we're kind of opposite.
Any cosmological model of the origin of the universe should ideally address the issue of why was the entropy so low at the Big Bang?
That's a good question. That's an excellent question. And I don't know, is the answer.
The entropy in the early universe is small because there was no particle production yet. And once quantum effects in strong gravitational field start particle production, then entropy grows.
If you do have this bigger universe, then of course you could radiate away things into this bigger universe. So the problem in cosmology, like in 4 dimension, is, I mean, you have one universe and then everything is trapped in there, right? You cannot get rid of entropy. But let's say, imagine you have, say, a planet like Earth, for example. Like, if it's just sitting in vacuum, just going to emit all this energy and it's going to go sit in a very low entropy state. The same thing with the sun. Eventually, the sun is going to run out of fuel and becomes a white dwarf and then radiates away all its energy. So that's the nice thing, is that you could get rid of a lot of entropy in that way if you have basically essentially somewhere that you can dump everything. And if you have an extra dimension, that's where you could do it, right?
In our film on conformal cyclic cosmology, Roger Penrose claimed that black hole singularities and the Big Bang singularity are quite distinct, as they have radically different types of curvature. One called Weyl curvature, which measures things like the strength of gravitational radiation, and the other called Ricci curvature, which is due to matter curving space. In black holes, it's the Weyl curvature that's infinite, but at the Big Bang, it's the Ricci curvature.
So let me start by saying that Roger is absolutely my hero and my role model, and I take his criticism very seriously. Roger's argument is that the Weyl curvature in the final singularity can't turn into Ricci curvature to become the initial singularity. But it seems that if there are strong enough quantum effects, that's not the case.
This goes to the heart of why we needed one extra dimension to do this. It just says that universe is homogeneous, but black holes are very inhomogeneous. That's just all there is to it. So universe does become singular, but in a very special way, because it's very uniform. It just everywhere together, density becomes very high. But black holes, its singularity is much more chaotic because it is very inhomogeneous. In fact, even now we don't really know how the singularity of black holes look. There are like simple toy models, but the mathematicians argue about exactly how singularities of black holes look like. So the reason then why we invented one extra dimension was basically we knew, of course, black holes are very homogeneous. But first of all, we kind of try to avoid everything inside of the black hole. We just say that our universe sits outside of it. So when we excise singularity, we don't just excise singularity, we excise everything. We get rid of everything inside where the horizon of the black hole would be. So all the places where the gravity can go crazy, we say actually it doesn't even exist. And the way we make things uniform is just by sitting on a membrane that hugs the black hole, basically. And that's much more uniform than what the singularity would be.
If our universe came from a black hole in another universe, where did that universe come from? Could the sequence extend forever into the past?
My job is to push back or push forward our understanding just a little bit to make some progress. And for me, it would be enough to push our understanding of the universe from just after the Big Bang to just before the Big Bang. Now, in the cosmological natural selection, I hypothesize that there are many Big Bangs because our universe is finely tuned for complexity and indeed for life. And this must have taken many generations of natural selection. But was there a first universe before which there was nothing, there was no time? Does that idea even make sense? But does it make sense to imagine that as far back as you go, there was something and there was time? These are questions which to me are beyond the ability of us as scientists to answer now. At least they're beyond my ability.
If our universe was born in a black hole existing in some parent universe, then that parent universe might have been born in a black hole existing in grandparent universe, and so on. So we could extend to some infinity in the past. So this is a possibility, and this possibility is beyond our observations because we cannot go back even to our parent universe, because going back to our parent universe, in which the black hole which formed our universe existed, would be going back through the event horizon, but we know that motion through event horizon is one directional.
There is this idea of epochs, and there's an expansion of the universe and then a contraction, followed by another expansion, another contraction. Whether time has a beginning is a different question, because you can have many bounces, but you can still have an initial bounce. The models that we usually play around with, time does have a beginning. Actually, currently we're thinking about models in which time can go infinitely, you can go infinitely backwards in time. The question is still open in causal sets.
Could you say anything about where the mother universe came from?
Yeah, that would be fun, wouldn't it? But that would be a realm of science fiction. I don't have anything to say about that.
CNS and eternal inflation are in some sense rival explanations for the purported fine-tuning of the universe. In eternal inflation, life exists as an inevitable winner in the cosmic lottery because there are so many universes and we have to be in the one that permits life. In CNS, life arises out of a selection pressure, much as in Darwinian evolution. But an advocate of eternal inflation, Leonard Susskind, has criticized CNS by claiming that the baby universe would have no memory of its parent and therefore wouldn't inherit its characteristics.
Why would Lenny say that? He doesn't know. What Lenny is pointing out, which is perfectly true, is that the theory that I described is based on an assumption. An assumption is that there is some memory of the parameters of the standard model when you go through the bounds. But it's basically a hypothesis. In this, it has the same status as the hypotheses that Darwin and people at that time made about heredity, where they didn't have a mechanism. Where later, most of those hypotheses were held up, but when DNA was known and understood.
Another criticism is that CNS isn't really like Darwinian natural selection, as there is no problem of scarce resources for a baby universe.
There is not a problem of scarce resources, but the problem of scarce resources is not a necessary part of the logic of natural selection or of population biology. What's needed is differential fitness, reproduction with small changes in the parameters.
While CNS and torsion claim compatibility with data from the cosmic microwave background, the holographic Big Bang may be in trouble.
Our best predictions for this model right now are in tension with data. And basically we did a very thorough job, so made a prediction. We had a very concrete model of infalling atmosphere, that how much fluctuations it produces, and we fitted it against Planck data, which is the data from the cosmic microwave background. A simple constant color model fits better than our model, which is kind of much more sophisticated. That's the status right now. Now, how that's going to change, I mean, depends if you can either modify our mechanism or have a different way of generating fluctuations. Our predictions for cosmic microwave background is not the thing I'm most proud of for this model. But the thing I'm most proud of is the geometric nature of it, is how it kind of uses the similarity between black holes and Big Bang, basically. If this is to be a successful theory, it needs to be modified, I think, yeah.
It would be nice if somebody more knowledgeable, a better astronomer, astrophysicist than me, came up with some more testable cases. Every few years I go back and I think about magnetic fields as one, or axions, or dark matter, or try to find some new way to make a test of cosmological natural selection. And I'm embarrassed to say that I haven't come up with anything new in a few years, and that's certainly been frustrating. For me, it's very important that by its very existence, it establishes an example of the way that time and evolution and evolving laws could play a role, the idea that the laws are changing, could play a role leading to a more explanatory physics. There are some general arguments which I made in the book with Roberto Manguiber-Unger and my other book on time about why we should look for in physics a theory in which the laws actually are not fixed and change in time. And there are arguments that Roberto and I gave that would lead to a more testable science, a more verifiable science. And this serves as an example of that general case. But it would be even nicer if it were falsified cleanly, because it doesn't happen very often in the life of somebody who studies quantum gravity and fundamental cosmology that you can have a theory which rises to the level of being falsifiable and then is falsified. Even better would be if it wasn't falsified.